Hi and welcome to the channel. This is the second part of the video roadmap series related to becoming a machine learning engineer or data scientist. As a reminder, here we have already covered the first part that was related to math. Right now we're going to take a step further and discover software engineering essentials that you need to study and master in order to become a data scientist. Let's go! Before jumping into details regarding software engineering, I propose you to take a look at the following diagram that covers the relationships between the most important domains used in creation of digital applications. As a general rule of thumb, when you work in a team of software engineers, most skilled backend and DevOps engineers can take the model that was developed by you and plug it into the application layer and make it possible to interact it with the database, to feed then all the data into the model, or allow the automatic deployment. Of course, you can rely on other engineers to perform these tasks, but in my opinion, it is much better for you to become independent and develop cross-functional skills. This won't only make you more confident, but will also make you more valuable on the market as a machine learning engineer. In reality, many software engineering companies and startups especially expect data scientists and ML engineers to be able to contribute across different stages of application development. So it can be no surprise if from time to time you need to do something on the backend side, or for example to set up a DevOps pipeline, or even go further and do something in the front-end interface, which for example had already happened to me. That is why it is necessary to still have a basic cross-functional expertise. So to summarize here, you firstly become more independent, you become more valuable, and your profile becomes more attractive. Then you are able to handle diverse tasks, and then it becomes easier for you to make a career change. There are many programming languages and no one can consider it the best, as each of them serves its unique purpose. However, when it comes to data science, Python becomes the number one choice for most professionals. Python offers an abundance of data science tools and user-friendly machine learning libraries, enabling efficient development of data science projects, while other popular languages like Java or JavaScript also provide implementations of machine learning algorithms. In reality, they are harder to use. And also another advantage of Python is its elegance and simplicity of syntax that makes it easy for beginners to use and master, enabling the earlier creation of complex pipelines and projects. As you can see on this diagram, the Python roadmap for beginners doesn't contain anything particularly unique, and aside from certain Python-specific concepts, it would be very similar to the roadmap for any other programming language. Now, let's discuss algorithms and data structures. Data is like fuel, and it's essentially what drives data science. Given that, there are numerous ways to process and handle data. But why would you care about them? Treating data inefficiently is like choosing wrong fuel for your car. While the final objective can still be achieved in many ways, it can come up with significant costs, excessive memory usage, and computational overhead. As a consequence, the entire system can fail to scale effectively. Now let's discuss several important topics that you need to study. First and foremost, it's the big O notation, which is widely used to estimate the overall complexity of algorithms. Using time as a metric for measuring algorithm performance is not ideal, since the same algorithm can behave differently in various environments. For example, it may run quickly on a powerful computer but very slowly on a computer with fewer CPU cores. Additionally, execution time also depends on the input data parameters. For these reasons, the big O notation was developed. It measures algorithms' complexity as a function of the input parameters, considering performance in a theoretical limit. The advantage of this approach is that each algorithm has a single level of complexity, regardless of the external conditions under which it is executed. Secondly, there are sorting algorithms, which play a fundamental role as they are frequently applied in practice and often serve as building blocks for many other algorithms. I would suggest that knowledge of the 5 most popular sorting algorithms is a very good starting point. Personally, I would strongly recommend learning about merge sort, as it introduces the important divide and conquer method, which is widely used in many other algorithms. Additionally, quicksort is worth studying as well, as it's known to be one of the most efficient sorting algorithms in practical applications. The next step consists of learning classical data structures. Doing so will make it easier for you to select the most efficient data structures for everyday problems, or even design your own based on the valuable knowledge that you have already gained. In my experience, the best way to deeply understand data structures is to manually implement them yourself without relying on any external tools or libraries. Now let's go to dynamic programming, which is a powerful technique that involves solving a problem by recursively breaking it down into smaller subproblems. By storing the results of these solved subproblems, the algorithm can then reuse them to find the solution to the original problem using recursive relationships between the subproblems. In my opinion, dynamic programming is one of the most challenging topics in algorithms, but it also provides extremely efficient solutions to problems that would otherwise require iterating through all possible solutions, often resulting in exponential or even factorial complexity. Here you can see a dynamic programming example where the goal of the algorithm is to find the value of the cell at C3. The known relationship between cells consists of recursive equations where each cell is the sum of certain cells located to its left or bottom. The algorithm recursively descends from C3 to the H cells on the left and bottom. By knowing their values, the answer is then iteratively calculated from left to right and from bottom to top, using the recursive formulas until the algorithm reaches the initial cell C3 for which it returns the final answer. The final chapter in the algorithm sections that I recommend beginners to focus is on graphs. I have already highlighted the importance of graphs in part 1 of this series when discussing discrete mathematics. However, when it comes to algorithms, I want to emphasize the importance from an implementation perspective. While understanding the fundamental concepts of graphs is a crucial aspect of discrete mathematics, applying them effectively in real-world applications is a completely different challenge, one that comes with its own set of complexities and pitfalls. There are many ways to write and organize your code. The two of the most popular of them are procedural programming and object-oriented programming. Simply put, procedural programming focuses on using functions as the main building blocks to organize the code. While this approach was highly popular in the past, it has become less relevant now, as other, more modern ways of writing code have emerged. In contrast, the object-oriented approach takes a step further. It involves representing code entities as objects that can interact with one another and have various relationships. These objects are defined through classes, which serve as general templates and may contain a combination of basic fields and other objects. Additionally, objects can exhibit behavior through functions that are also called methods implemented within the classes. One of the advantages of object-oriented programming is its natural correspondence between objects in code and how those objects are perceived by humans in real life. Additionally, it's easy to reuse classes and objects, making the code more maintainable and reusable. Object-oriented programming is built on three crucial pillars that are called inheritance, polymorphism, and encapsulation. While we won't dive deeply into these terms here, they can be summarized as providing additional functionality to further reuse existing code within classes while ensuring its safe and consistent usage. Now it's time to talk about databases. To be used efficiently, data is stored in databases. They already provide all the necessary functional layers that include security configurations, read and write optimizations, transaction management, and many other features. For data scientists, the most common use cases involve database creation, reading data from them, and writing data. Before exploring specific technologies, it's important to distinguish between two types of databases: relational, that are also commonly referred as SQL databases, and non-relational or NoSQL databases. In simple terms, relational databases organize data strictly in a tabular format, similar to how humans typically organize information in the real world. On the other hand, non-relational databases are less strict and impose further constraints on data organization. Both SQL and NoSQL formats have their own advantages and disadvantages. For beginners, I believe it's essential to focus heavily on the SQL language. SQL is the standard language used for managing almost all relational databases. Specifically, a data scientist is expected to know how to perform the four basic operations: create, read, update, and delete data in tables. While the create, update, and delete commands are relatively straightforward to use in SQL, the select operator likely plays a much more critical role. Select is widely used in practice and offers numerous ways to retrieve the necessary data efficiently. I would say that for the most learners, it doesn't matter which relational database you choose in order to master it, as all of them behave almost the same on the basic level. So you can pick up either Microsoft SQL Server, Postgres, or MySQL. It doesn't matter. For non-relational ones, I recommend you picking one or two of them, like MongoDB, Redis, Neo4j, to fundamentally understand the difference between the relational and non-relational databases. Speaking of web development, I would say that is an optional part which is not directly related to data science. Of course, as a machine learning engineer, you must be able to construct a predictive model and deploy it. But it would be a nice to have skill if you can also be able to visually present it in a beautiful interface to somebody else. And as I told you before, many companies and startups right now expect machine learning engineers to have cross-functional expertise, which is also very valuable. Moreover, by understanding the structure of an HTML page and how the web works in general, you can perform web scraping by automatically creating scripts that parse information from web pages. This information can be then used to train models, for example. And finally, solid web knowledge enables you to make external API calls to other services. This is especially important in the modern era with powerful LLMs like OpenAI models, Mistral, Google models, Perplexity models, and so on. In general, obtaining a basic understanding of web development is a relatively achievable goal. To get started, you should learn HTML, which is used to construct the main structure of web pages, CSS for making the interface more stylish and responsive, JavaScript to add dynamic interactions and animate websites, HTTP protocol, and how to make API requests using JavaScript. And as a bonus, you can also learn one of the classic front-end frameworks like React, Vue, or Angular to accelerate the development process. And with this knowledge, a data scientist should feel confident in performing basic web-related tasks at work. DevOps is another branch of software engineering that focuses on development optimization. Generally speaking, DevOps engineers construct and set up pipelines. They automate deployment processes, saving time for software engineers while they can focus on implementing more important product features while focusing less on the deployment. Nevertheless, there are certain tools that data scientists should master to make their workflow more efficient. In a vast majority of enterprises, Linux is used as the main operating system for application development and deployment. For this reason, it's common for developers to use the Linux command line in their daily routine tasks. Examples of such tasks include navigating through a directory structure, changing file permissions, managing processes, executing scripts, and sending or receiving data from remote servers. All of these tasks are performed using Bash. Bash is a scripting language which has a lower level syntax compared to other programming languages like Python and may not be as convenient to use, but it still provides a lot of useful functionality, especially for managing operating system tasks and state. In most cases, for data scientists, knowing basic Bash commands is enough. Another important tool to master is Git, which allows for version control of the entire code base. By using commits, a developer can easily roll back to a previous version of the code if, for example, something goes wrong with the current one. In addition, Git is a collaboration tool that enables developers to work together on multiple features of the project at the same time using branches and ultimately merge all the changes together. When learning Git, it's also beneficial to get hands-on experience with a cloud version control system. The most popular ones are GitHub, Bitbucket, and GitLab. Personally, I would recommend using GitHub as it's the most widely used one. With the cloud version control system, developers can publish their code to a central repository, making collaboration easier. They can also create issues, use Kanban boards, write comments, and organize pull requests to merge changes. For more effective collaboration, it's also important to be familiar with the most common workflows when using Git. One of the most popular of them is Git flow, which defines several types of branches and the rules for how they should be managed. Finally, another important tool is Docker, which is used for application containerization. Every application, when deployed, requires a unique set of dependencies that may demand specific versions or properties of the operating systems where the application runs. And to avoid compatibility issues, Docker comes into play. By being compatible with various operating systems, Docker isolates the application in a separate environment and acts as an adapter between the system and the application allowing all necessary dependencies to be downloaded. As a result, the same application can run within the Docker environment on different operating systems. While many other roadmaps might not explicitly mention this, I find it still important to say for beginners that there are several data formats that you need to understand, like HTML, XML, CSV, JSON, YAML, or Markdown. In this video, we have identified and talked about crucial software engineering domains and concepts that you need to master in order to become a data scientist. And as I talked before, data science is a very broad domain and demands a diverse skill set. But if you gain solid understanding in math, about which I talked in the previous part of this video series, and in software engineering, machine learning development will become much more accessible to you. And by the way, we'll talk about the machine learning skills in the next part of this video series. And as a final advice, I want to strongly recommend you not to only focus on theoretical concepts in programming. This is one of the errors that beginners make. I want you also apply the real skills that you learned recently in real-world projects. It will help you a lot to solidify the understanding. And with that said, I want to thank you for watching this video. I hope you really enjoyed it and were able to get many useful insights. See you next time. Bye.